Hey guys, welcome back to my YouTube channel, Steve Learning Note with me, Steve. I'm a software engineer from Indonesia. I like to share my learning note in this YouTube channel. So if you like this kind of video, subscribe and turn on the notifications. In this video, I'm going to share about Internet Protocol. These are the topics that I'm going to share with you, starting with IP package, hop, time to leave, MTU, IP fragmentation, ECN, AQM, FQ-CoDel, ICMP, ping, Traceroute, and ARP. So, Internet Protocol. It's something inside the layer 3 inside the OSI model. The purpose is to find the best path to send data across network using IP address. So inside this layer, our data that comes from the applications will be encapsulated in layer 4, either by segment or datagram, depending on your protocol choice. And then in layer 4, your data will have the ports. Meanwhile, in layer 3, your data will be encapsulated using IP package. And that package will give you IP address. So IP package is a unit of data sent over the internet at layer 3 to route data between networks using IP address. So the package has header and the payload. The header size is between 20 to 60 bytes. So minimum size is 20 bytes, but it can be extended up to 60 bytes. And the payload has this maximum size. So this is the structure of the header, right? So how to read this? So this number is bit, right? And one row is 32 bits. So now we have 1, 2, 3, 4, 5 row. Each row has 32 bits. So 5 times 32 is 5 times 160 divided by 8. So it will be 20 bytes, right? So that's the minimum size of the headers. But if it has options, it can be up to 60 bytes. So the first 4 bits is for version 4 or version 6. And the next 4 bits is for IHL. This is the header line. The minimum size is 5. And then next we have the SCP. The SCP is for type of the package, like a VoIP, for example, voice over internet and something else. It is used for prioritizing the package. ECN is for to notify the sender about the congestions. We are going to discuss about that in detail later. Total length is the total length of the entire package. And everything in the second row is for IP fragmentations. That is something that we are going to check together. Time to leave. This is also something that I will share with you. And protocol is the number, denotes the protocol types that this IP package has, right? It can be ICMP, for example, TCP or UDP, etc. Header checksum, and then source and destination addresses, right? And this is the offset. So this is the first 32, the second 32, and so on and so forth. Hops, like rabbit can hop from one place to another place. So your package can hop, right? So for example, sender A want to send the data to B. Hops mean every device in the middle between the source and the destinations, such as switch routers, right? So in this case, we have 2 routers in the middle. So in this case, when A send data to B, it will have 2 hops. 1 and 2, right? There is a case where the data is just circling around between the routers because misconfigurations. That is called hop loops. And imagine that there is a lot of data coming into this route, and these routers are misconfigured. So there are a lot of data that will just looping around in the cloud somewhere. So we need to find a way to drop this kind of package, right? That's why we have time to live. Time to live is basically just a number of a limit of hop. So it's a number that represents a hop limit that prevents package from circulating endlessly in networking routing loops. So it's just a number. So when the package travels to a layer 3 device like router, the number of TTL will be decreased by 1. If it comes to router, which is layer 2 device, switch layer, which is layer 2 device, the TTL will not be decreased. It's just for layer 3 device. And when the number gets to 0, the package will be discarded. And then the router will send ICMP time exceeded message to the sender. That's the mechanical. So hops, so A send the data to B. So this package will have TTL number 128, for example. So the number here can be configured depend on the sender. Usually the number depends on the operating systems. And then when hopping and then reach to the layer 3 device, the number decreased by 1, and then the number decreased by 1 again. Now, your package, right, is in layer 3, okay? And then in layer 2, there will be frame, right? So this is frame from your network device. So your IP package will be encapsulated with frame, which will give you the MAC address. So the frame has the maximum size, which is called MTU, right? So your IP package cannot, the size cannot be greater than the size of the Ethernet frame, right? For example, we have the Ethernet frame, right? So what happens if the packet size is greater than the MTU size? There are two options. First, don't fragments mean that the router will drop the package. So for example, a router receiving a package from somewhere, and then it detects that the router's device MTU is smaller than the IP package size. So the router can decide to drop the package and sends ICMP error back to the senders. I will explain about ICMP later. And then later the sender reduces the size and retries. There's second options to fragment the IP package if fragmentation allowed. If every party in that route support fragmentations. If that happens, router can split the package into different packets, into smaller packets, so that it can fit into a single frame. And then the final destination host will reassemble these fragments together back into one IP package. So let's see. As I told you before, the second row of the headers manage everything about the fragmentations. We have the ID, which is the ID of the fragment. So the ID will share the same ID if it comes from the same IP package. Flag, it has two kind of flags here, DF and MF. DF means don't fragments, and the value is number 0 or 1. 0 means false. Don't fragment, false. It means that the device supports fragmentations. If the value is 1, means that the device disable the fragmentation or doesn't support fragmentations. MF means more fragments. 0 means there is no more fragments coming in, which is this is the last fragmentations. 1 means there is more fragments coming. So you need to wait. And the last is fragment offset. So this is the offset number of the fragmentations, right? Because we need to chunk it down and then we need to know the positions, right? So this is the offsets of that chunk positions in 8 bytes unit. So let's see the illustrations. On the left, I have a simple code written in Python using SCAPI. SCAPI is a library to simulate networking things. So I have a big package of A times 3000s. And then I will fragment it using fragmentation size of 1500. And then I print the metadata. So it turns out it is split into 3 fragments, 1, 2, 3. As you can see, the ID is the same, 1 and 1 and 1, because it comes from the same IP package. And then you can see the offsets. The offset number is different. This offset is in bytes. And then you can see the value of MF flag, total package length, and payload length. And then if we draw this into an illustrations, it's something like this. So we have the original package of 3000 bytes, right? From index 0 until 2999. And then we chunk it, we fragment it, right? This is the first fragment. And then this is the second fragment. And then these are the third fragments. So the final destination host will wait and reassemble this fragmentation together back into one IP package. Right, so that is the fragmentations. All right, congested router. All right, sometimes router can receive a lot of traffic, spike of traffics, and then the router has a device computation limitations like limitation in the memory and CPU and stuff like that. So at some point of time, if it gets a lot of traffics, the router performance will be dropped. So what happens if there is a congestions happening in the router? That router can decide to drop the package because its buffer is full. And if it does that, right, that sends the data using TCP for the sample, it never receives the acknowledge message over here. So it waits until timeout, TCP timeout. Only then A can predict a network congestion, and then A reduce the rate. So it's not really efficient because A needs to wait until the TTL to retry, right? So therefore, we have something called ECN. It stands for explicit congestion notifications. So it's a mechanism that allows network device to signal congestions without dropping package, right? That's awesome. So this is controlled by these 2 bits flag over here, right? This 2 bits header is a combination of 0 and 1. 0, 0 means that this device is not capable of ECN. Combination of 0, 0, 1 or 1, 0, it means that this device is capable of doing ECN. And if the value is 1, 1, it means that it is experiencing congestions. So how does it work? So if A support ECN, then it will send the data, the IP package with ECN header value of 10 or 01, right? send it to this router. This router have congestions. So my buffer is about to be full, but I support ECN, so I will forward this package instead of dropping it. But I will let you know that I'm having congestions by updating the header value using ECN value 11. So this package will be forwarded to B. B receive it and send the reply message to A. A will receive the package with the ECN 11 header. So it knows that there is a router having congestions. So A hopefully will reduce the rate of sending the data. In that case, router needs to have an algorithm to detect early congestion, right? Meets with active queue management, right? It's a technique that prevents network congestions and high latency by intelligently dropping or marking package before queues become full. Because we cannot do it with a simple FIFO algorithm. We need this kind of algorithms. And one of the common algorithms in this area is called FQ-CoDel or Fair Queuing Control Delay. It's an algorithm that combines two algorithms, FQ, Fair Queuing, and CoDel, Control Delay. So let's take a look one by one. Fair Queuing. So let's see if the router doesn't have fair queuing. Let's say we have four kind of data package. A for bulk download, B for web browsing, C for video streaming, D for voice over internet. So if it doesn't have fair queuing, it will have a single queue. This single queue is a FIFO algorithm. We'll process the package one by one, first in, first out, right? So the problem here is that A for bulk download will have more package than the other type of package, right? So that A will get the most bandwidth. And the rest, B, C, D, will suffer high latency because it needs to wait, right? So now we have fair queuing. In fair queue, every type of IP package will have its own queue. Well, to be exact, the mechanism is not like that, but it's just the overview. I will get more detail about it, right? So just pretend that every type of package will have its own queue, right? A, B, C, D will have its own queue like this. And then there will be a round robin scheduler. So this round robin will pick the package one by one. Not exactly one by one, but I will tell you more about that later. For now, let's assume it will pick one by one. So it will pick A, process it, B, process it, C, and D, and back to A, to B, to C, to D. As a result, each flow gets fair shares, right? Large flows cannot monopolize, and small flows stay responsive. That is fair queuing. So, how does flow or that queue is identified or created? So it's created by using 5 tuple hash. A hash of source and destination IP address, source and destination port, and then protocol. This combination will make one queue or one flow, right? When one flow uses larger package, it unfairly dominates the bandwidth. This causes starvation for flows with smaller package. Okay, so we have divided the package into different flows, but the problem still remains. If one flow have a package size larger than the other flows, the starvation can still exist. So how we can solve this, right? So the round robin scheduling is not just pick one from this and then pick one from there, but we use deficit round robin. It's a fair scheduling algorithm where each queue can send packets as long as its accumulated byte, credit, or deficits covers the packet size, ensuring fair bandwidth sharing regardless of packet size. So the round robin algorithms consider the size of the package. It has terms of quantum. The terms of quantum in this area, it means the maximum number of bytes each flow is allowed to transmit per round to ensure fair bandwidth sharing. So, for example, if we have three flow A is for bulk download, flow B is for web browsing, flow C is for video streaming, and we have quantum size of 1500 bytes. And each package in A has 1000 bytes, 300 bytes, and 700 bytes. So let's see how does it work. So first, in the first round, it will get one package from A, right? A has 1000 bytes, so it can process only one, right? And then it has deficit of 500 bytes, right? It cannot process more because it requires another 500 bytes. So this deficit will be kept. It will be safe for the next round. Next, the second round for B. B has 3 packages, but it has small size, each 300 bytes. It means it can process all of that 3 in the same round, right? Because it's less or equal than 1500 bytes. In the third round, it will take 2 packets from C, right? 2 packets, so it's only like 1400. So it has deficit of 100 bytes to be used for another round. Round 4, now it's a turn again, right? So now in the next round, it has 1500 bytes plus the deficit bytes from the first round. So now it has 2000 bytes. So it can process 2 packets in the same round. And then finally, the fifth round, it will process the remaining packets in flow C. So that's how deficit round robin works. All right, even with fair queues, queues can grow too long. Enters CoDel. So what is CoDel? Let's see. In CoDel, a full queue is fine as long as it empties quickly. So if a router has a spike of traffic, but it can process that fast, it's fine. It's not a problem. It will not make the router congested. A queue is bad when packets sit too long. That's a problem. Right, let's see the concept. So in CoDels, there is a concept of sojourn time. So it's basically time package spans in the queue. So example, if the package enters at time 0 and it leaves at time 30 milliseconds, so the sojourn time will be 30 milliseconds. And CoDel has several configurations, and one of the tools are target and interval. If target 5 milliseconds and interval is 100 milliseconds, it means that if sojourn time greater than 5 milliseconds, greater than the target, continuously for 100 milliseconds, it will drop or mark the package if the ECN is enabled. Alright, so if the router have temporary congestions, like this, right? At time point 20, it has temporary congestions. the delay time, the threshold, the target is 5 milliseconds, right? It's greater than the target, but it's temporary, right? Because after that, it's going down. At times 20, surgeon time is greater than 5 milliseconds. Yes. So there will be a variable called first above time. So first above time is when it detects the delay or the surgeon time above the target time for the first time. So the value variable is 20 millisecond time point in this case. Now we check on the 40 time point, right? 40 minus first above time, right? Minus 20 is not equal with the interval. So the interval is 100 millisecond. It means that it continue, right? The package will not be dropped, right? Because let's go back again. Because it will only drop or mark package if it's continuously above the target time for 100 millisecond, right? Right. Now at 60, surgery time is already less than 5 millisecond. Then it will reset the first above time. Now what happens if we have consistent congestions? Like this. It looks bad. So at time 20, surgery time is greater than 5 milliseconds. So first above time will be set to 20 milliseconds. Next, at 40, right? 40 minus first above time is not equal with the interval, so it continue. Package is not dropped, right? And then it will start counting that until 120, right? We just skipping, okay? So I will skip to 120. In 120, it will calculate again. 120 minus first above time 20. So now the value is equal with the interval 100 milliseconds. It means now is the time to drop the package or mark the package with the ECN 11 during or for the package at 120 millisecond time point. Why? Because it's still above 5 milliseconds. Right? So from 120 to 20, when we met with the first above times, the interval is 100 milliseconds. So what happened after that? The congestion is still happening, is still continuing. Something like this, right? If bad delays continues, feature drops happens at shorter interval. So it will not be at 100 millisecond interval, but it will be shorter. So how does it calculate that? So drop next is a variable when the router will drop the next package. The formula is time of last drop plus interval divided by the square root of drop counter. So time of last drop is 120, right? From the previous example, we drop a package or mark the package right at this time point plus the interval 100 divided by the square root of 1. This is the drop counter. How many drop that it has dropped in this continuous 3 congestions durations? 1. So the value is 220. It means that when it arrives at time point 220, this is the time for the next drop, right? It will drop or mark the package that coming at this time interval, at this time point. So it means that interval now is no longer 100 milliseconds, but it's 80 milliseconds. It's faster, right? So if we combine FQ with CoDel, is basically we have pair queuing, right? And then on each flow, on each queue, it applies CoDel algorithm to mark which package that needs to be marked or dropped. And then we will have the deficit turn bin, scheduler, and then finally the output. So for summary, FQ-CoDel detects congestion early by measuring queue delay, not queue size. And instead of dropping package, it can mark them with ECN to signal congestion before things get bad. Why this is called early congestion detections? Because FQ-CoDel reacts when delay greater than 5 milliseconds in this example, not when queue is already full. So it can detect early. Moving on to ICMP. ICMP stands for Internet Control Message Protocol. So it is another protocol inside protocol. It's designed for informational message. It lives in layer 3. We have seen some example before, if you are aware of that. First, during the explanation of time to live, if the time to live number gets to 0, the router will send time exceeded message. That is ICMP protocol. When the packet size is greater than the MTU, that router will send error of fragmentation needed. That error is in the form of ICMP. And there is another example. For example, destination port unreachable or something like that. Okay, there's many type of message in this protocol. Right, so there, the protocol. So the protocol, as I said before, it's a number, right? For example, if the number is 1, that is for ICMP. So this is the header of ICMP message. It has type, code, checksum, and the rest of the header. So type is number like 1, 2, 3, and code is a code. Code is kind of like a subtype of type. So for example, type 3, it is for destination unreachable, and the code is from 0 to 15, right? And then each of code has different meanings. 0 for destination network unreachable, 1 is for host unreachable, and so on and so forth. Let's discuss about ping. Why? Because ping use ICMP actually. So if A want to send ping request to B, right? A with this IP address want to send message to this B, right? To this computer, right? It actually send IP package with protocol 1 ICMP of echo request, right? So the type and the code is echo request, and it has TTL. It send that package, and then it will be received by B, right? Yeah, B now receive the ICMP echo request, right? And then B will reply that with ICMP echo reply type message, and then it will be received by A. So here I have example of doing ping using WSL. I ping google.com. So ping command actually needs IP address. So if I use domain name, it actually doing DNS first to get the IP address. Right? So I ping google.com, right? This is the IP address of google.com. And then this is the bytes that we receive from Google, right? The bytes of ping reply. And then this is the sequence of the ping request that we send, 1, 2, 3, 4, 5, 6. And then this is the TTL, right? TTL that I received from Google, right? So the TTL has been decreased to 109. And this is the time it needs to travel round trip from my computer to Google and from Google to my computer. All right. So now we know how to read these stuffs, right? And now we know understand how these stuffs works. What is that TTL? What is the TTL means here, right? So that's the idea of learning. Now, at the other hand, I have another example using my Windows machine doing the same thing, TTL. I got replay from Google, right? And then I get the time, I get the bytes. And then if you notice that actually the bytes that we receive in Windows and Linux is different, right? Do you know why that? Because I think the header size is different for Ubuntu or Windows, maybe. I don't know. Right, the time and the TTL. The interesting here is that the TTL from my Windows machine is 110. Meanwhile, in my WSL is 109. Windows One has one more TTL, right? Why does WSL have one more hop? Right? That's the question that we will try to answer by using these tools, Traceroute or Traceroute in Windows. Traceroute is a network diagnostic tool that maps the paths or the hops package stack from the source to the destinations. It uses TTL by sending incremental TTL. So how does it work? All right, so A sends echo request to B, right? But if you notice, the TTL is 1, right? So what happened that it goes to this router. Because the TTL is just 1, it will get 0 when arriving to this router, right? So this router will send back a destination unreached ICMP message back to A. When that happens, now A knows that, oh, in my route, there is a router with this IP address, right? That's cool. So next, A try to send another request, ICMP echo request, this time with TTL2. It will be received by this router. TTL will be decreased by 1 and then will be forwarded to the next router, to this router. TTL will get to 0. So this router will send back a destination unreached message back to A. And A will receive that message. It knows that there is a router with IP address along the way. And then finally, A send another message with TTL3. And then, long story short, the message will receive by B, right? So A, with this traceroute, now knows that between me and B, there are 2 routers in between. So that's traceroute works behind the scene. So for example, yeah, I'm going to show an example here. So in Linux or Mac, traceroute use UDP protocol by default, but we can change it to ICMP echo ping, right? Or TCP if we want. But in Windows, if we use traceroute, it will use ICMP echo ping and cannot be changed. So on the left, I traceroute to google.com, right? Like this. And then it receives numbers like this. So my request received by this IP address first, and then after that it received by this IP address first. And then if we see the Windows one, I'm doing the same thing. My first request will be received by this IP address first. So this IP address 92.16.8.3.1 is my router at my home. So this is my router. This is my router, and this IP address is actually a virtual network inside the WSL, right? So that's why the number of hops for my WSL has one more than the Windows one, because it needs to traverse. It is coming in from the routers and then go to my Windows machine, and then inside my Windows machine there is a virtual network for my WSL, and that is this IP address over here. That's the gateway for my WSL. And then eventually it will reach the Google server over here. So there is bunch of IP address here, but I block it. I don't know if it's safe to reveal it to you. And it has this star star star. It means that this device either drop or doesn't support the ICMP, right? ICMP can be blocked for security reasons by firewall, for example. It doesn't want to reveal itself. Right. So here we go. What else? So if you see, there are 3 times here. So on every traceroute, it sends 3 times. So we can check the average of latency if you want. All right. How does a device find the MAC address of another device when it only knows the IP address? So in layer 2, we have a data layer, and data layer is mainly for the same network communications. And for doing that, we need MAC address of the next destinations, right? Meanwhile, our applications up until layer 3, we only know the IP address. How does our computer know the MAC address of another device? Right? So here in layer 3, we have the IP address, but in layer 2, the data link, which is control communication between devices on the same local network, it needs MAC address. So how we can get it? Meet with ARP. ARP stands for Address Resolution Protocol. It's basically kind of like a map, a translator between IP and MAC address for IP version 4, because IP version 6 use different mechanisms. So how does it work? So let's say A want to send data to C. So A will send ARP request saying that I'm looking for computer in this network that has this IP address. I know the IP address, but I don't know your MAC address. So if you are 92.68.1.3, please replay this message with your MAC address. All right, so B will receive it, D will receive it, C will receive it, but only C will replay it because it is its IP address. So that's me. Here's my MAC address, and this is my address. It will send the ARP replay. So after A get the ARP replay, it catch that data internally. So it has the mapping between IP address and MAC address. So next time I want to communicate with C, it doesn't need to send the ARP request anymore. So what happens if the destinations is in the different network? A want to send to X, which is in different network, right? So if you see the subnet is different. So I'm looking for 92, 168, 1, and 100. What is your MAC address? So this IP address is the gateway IP address, right? So A will have the X IP address already. It's doing the subnet computations, which I have explained to you in the previous video. As the result, it knows that the destination is not within the same network, right? So that's why it will send the request to the gateway, so that gateway can route that package to the destinations or to another router that knows the destinations. So that's why A will ask the MAC address of the gateway if it doesn't know. So router will send back the ARP replay. This is my MAC address. You can use it to send the request to me. So now A have the mapping of the gateway with gateway MAC address. So now A can send data to MAC address to the router, and router can forward that message, that data, to X or to another router that knows X in the network. Oh, that's the end of the slide. Alright, that's all that I want to share with you. I hope it's useful. Well, until the next video, keep learning and stay healthy. Bye-bye.